So today, let's talk about light. Isn't it pretty? I know, it's just so pretty. And we're kind of building up to talking about telescopes that allow us to gather light. Okay. So can you kind of see these tick marks in this rainbow? Kind of see the rainbow here? Those tick marks are kind of like, if you're familiar with a fingerprint, it's unique. Okay, if you're familiar with DNA testing, it's unique for people. Okay, those little tick marks are unique for a particular element. Okay, so actually those little tick marks are significant if you know what you're looking at. Just like DNA, things can be significant if you know what you're looking at. So Newton not only developed calculus, bless his heart, okay, and he not only came up with those laws of motion, but another thing that Newton did was to send what appeared to be just light from the sun through a prism. And he did it not by accident. I mean, he did it using the scientific method of discovery, thinking about it, coming up with a hypothesis. And what he found was, you send light through a prism, and the light is separated into colors. And not shown here, but what he did also then was to take one color of light, we call it one component of light, and he sent it through a second prism. Because he's like, hey, I wonder what happens there. And actually what he saw was its trajectory was bent or refracted, but it was still the same color of light. So when we talk, the next slide is a really busy slide. It's actually a figure that I'm going to go to next. And it shows light, but it also shows all these other types of energies that are cousins of light, collectively called electromagnetic radiation. Okay. So light is one cousin of electromagnetic radiations. The others you're going to recognize, like gamma rays, that's a cousin. Radio waves, cousin. Yeah, it's fun teaching over the years because I've added that term. I just think they're cousins. Just like cousins have similar characteristics, good, bad, and otherwise. Okay. So also these different forms of energy have similar characteristics. So here we go. Here's my busy slide. And I think to kind of emphasize this, I'm going to draw it over here a little bit to kind of highlight some of this. So I'm going to show you the cousins of light. And they're called electromagnetic radiation. Okay, so if we talk about a spectrum of light, you would tell me all the colors. That's a spectrum of visible light. Well, a spectrum of all different colors are called electromagnetic spectrum. So, for instance, we have visible light. Okay, and I mentioned gamma rays. Okay, those are cousins. So it goes visible. And notice how small the sliver of visible light is. And then it goes ultraviolet. Okay, then it goes X-rays. And then it goes gamma rays. Okay, different kind of sets of energies. And longer wavelengths goes like this. On the other side of visible, we have infrared. Infrared, I tell students, if you don't already kind of think of infrared, think of heat or thermal energy. And then we have kind of microwaves. There's a little bit of an overlap, and then radio waves. It's funny because, you think, well, what do radio waves and gamma rays have in common? And they are related, okay? But can you see how, I'll start over here, radio waves have the longest what we call wavelength. And I'm going to go ahead and tell you what the symbol for wavelength is. Remember the symbol for the speed of light is c, I don't know why. But the symbol for wavelength is lambda. And it looks like this. You kind of draw kind of an upside down V with a lid, with a hat. Okay, so that's lambda, that's wavelength. Longest wavelength, okay, and shortest wavelength over there. So they might be cousins, but their wavelengths vary significantly. Let me tell you how short gamma ray wavelengths are. Shortest, I'll go ahead and put lambda. Shortest lambda. How short are they? Well, underneath here now, you kind of see how short or how long they are. So I'm not going to make you do any calculations, but I do hope you kind of, when you see 10 raised to a power, you kind of get a sense for what that is. So over here, with regard to gamma rays, we have 10 raised to the negative 12th power. Okay, so wavelength is equal to 10 raised to the negative 12th, and that's in units of meters. So to unpack that, we'd put a decimal, and we'd put 11 zeros. No naked numbers. Okay? I mean, that's how small those wavelengths are. Those wavelengths, radio waves, 10 squared. Anybody know what 10 squared is? It is 100. Very good. Equals 100 meters. So to kind of put things in perspective, how big are these? The radio waves are about the size of a football field. Okay. The gamma rays are about the size of, well, they're smaller than a hydrogen atom. I don't remember what that little thing is. So you're like, what do I mean by size here, right? Well, one of the things we need to talk about with regard to electromagnetic radiation is, do you see the, almost looks like a slinky? So when I say the size is 0.00001 meters, or the size is 100 meters, the size of a football field, I mean how long does it take to complete one cycle? Because we're going to see that radiation, light included and all those cousins of light, what they do is they travel through space in waves, but they also have a particulate component to them. It's called the duality of light. All right. So then we get to frequency. And to me, the best way to think about frequency actually kind of goes along with wavelengths. Is frequency usually is per second. Frequency is per second. And basically, to count frequency, you stand here and you hold the counter and you only let it go for 1 second and you see how many cycles pass you. Okay, that's cycles in 1 second. Otherwise known as hertz. Cycles per second. So can you see where if they're really small, gamma rays, you get 10 to the 20th cycles in 1 second. That's a lot of cycles. Okay, so that's one with like 20 zeros after it. Okay. So, and the other thing, if you're waiting for a football field to clear you, it's still quite a few cycles. Okay, over here, 10 to the 6th, what that's help me out, 1 million. I'm good with that, right? Okay, 10 to the 6th is 1 million. So with regard to football fields, you get 10 raised to the 6th that pass you in 1 second. That's still a lot. Okay? So kind of what we've got here, I want to link frequency with wavelength for these. The symbol for frequency is F. Okay? So because they're so big, the frequency for the radio waves here, frequency is low. If you count a million, if you count 1 million as low, it's low. Okay, here the frequency runs in the neighborhood of 10 raised to the 6th power. Okay, and that is in hertz. It doesn't really hurt, but it's in hertz. And what that means is per second. Cycles per second. So then if we go over here, notice, like I said, the frequency here, kind of related to the fact that the wavelength's so dang small, is 10 raised to the 20th power, hertz, or per second. Cycles per second. So we have these cousins. And it's kind of interesting. Our sun, which is a star, is kind of an average star. Okay? Visible light, which we count on so much, is just kind of an average type of electromagnetic radiation. It's kind of like playing Goldilocks and the Three Bears, and it's always the average one. I don't know if that really works. So where do you find these cousins here on Earth? I think this is quite clever. Your author put down some kind of sources of these different cousins. But we're not as interested on Earth as we are in celestial objects. Okay, so that last row down there is why do we care about those cousins? And we're going to see that, for instance, in order to understand black holes, I'm pointing over here to gamma ray bursts. In order to understand black holes or neutron stars, or I guess that's probably the energetic events, we need to look in that high energy region. So guess what? If we have the most awesome telescope, okay, that's just that we can look through, it's not going to see this. So we need to modify our telescope to gather that energy. Okay, it's exciting. Then clear down over here, see the cosmic microwave background? Okay, this one, this kind of funky looking thing, this actually is kind of depicting the universe. Okay, from our perspective. And these long wavelengths, and actually it's related to the fact that that the universe is expanding. We need to look in long wavelengths to see the background hiss from the beginning of the Big Bang. Okay, so that's kind of where that goes. So put another way, only kind of in this region right here, okay, is our regular telescope's going to work. It's the pretty region. Okay. So, electromagnetic radiation. You kind of saw this, the up and down sort of thing. Now, to kind of talk about one repeating unit, one wavelength, okay, we can talk about from crest to crest or from trough to trough. But whenever you get that same part of that wavelength back again, you count that distance and that's your wave. Or once you get that same part of that wave. We talk about a crest to a wave, a trough to a wave. I don't know what the midpoint is, okay, but that's wavelength. So the dual nature of light, and I'm not going to necessarily emphasize it too much, but it's got that wave property and it's got a particulate property. And that particulate property, you see the word photons? I love that word photons. Okay. The particulate part is balled up in what we call photons, associated with a particular energy. So sometimes when, this is because it's just the way I think of it, sometimes when I'm out observing, I look at like Saturn through the telescope, I look at Andromeda through a telescope, and I think, I captured those photons. Okay. That took so long to get here, right? Okay. So cousins, different forms of electromagnetic radiation, okay, they differ in their wavelengths. Does that buy that? They differ in their wavelengths. If I were to ask you which one you don't mind getting zapped with, okay, you'd probably kind of veer towards this side, okay? And actually, I'll go ahead and kind of superimpose it on this. With regard to energy, these longer wavelengths have less energy. So put another way, I'm going to kind of go from right back to left. I'm going to put increasing energy. This would apply to the whole spectrum. Increase energy, E for energy. So the other day, when we were in here, last week, we talked about there are some times when nature, with the same object, you increase something and the other thing increases. There are some times when you increase something and the other thing decreases. It's like, for instance, we talked about gravity, and we say if you increase the masses of the objects that are attracting to each other, gravity increases, force of gravity. We said if you increase the distance between the object, what happens to the force of gravity? It decreases, right. That's called an inverse relationship. And we kind of have an inverse relationship over here. Because do you see where over here with radio waves, we have a long wavelength, big wavelength, and low frequency? And then over here with gamma rays, we have a short wavelength and what? High frequency, right? So they kind of vary. And this is going to show you that they're it's kind of nice mathematically how they vary. So I have, I think, 3 or 4 different wavelengths to kind of show you, examples of wavelengths. And in order to have this make sense with regard to frequency, I'm going to remind you or tell you, might have to look it up, but the prefix G means giga, and that means 1 billion. So when you see 30 gigahertz, you're talking about 30 billion cycles per second, 30 gigahertz. That's a legitimate frequency. Okay, that's 10 to the 7th. Okay, 3 times 10 to the 7th. Okay, wavelength is 1 centimeter. That's cool. So notice that if we go ahead and if we call the first one A and the second one B, notice what B is we took the wavelength and we shortened it by a factor of a half. Okay, we shortened it by a factor of a half or a 2, however you want to think of it. So we would expect with the wavelength shorter, the frequency would go up. And you see the frequency going up a factor of 2. So instead of 30 gigahertz, it's 60 gigahertz. It's a wonderful thing. Okay, one went down, wavelength went down, frequency had to go up. Okay, one more. Lots of squiggles, more squiggles. So if we compare the third line to the first line, okay, notice instead of 1 centimeter for the wavelength, it's 1/4 centimeter. Okay, so it's a factor of 4. And then notice then that the frequency is 4 times the original frequency. Okay, so it's 30 times 4, 120 gigahertz. So there's this cool relationship with regard to any cousin, and it can be summed up this way. Down there at the bottom, kind of a summary of what we have going on for any form of radiation. You can hone in on that radiation, and you can take its wavelength times its frequency. And this it's like, how does this work? But in chemistry, we talk about making sure you let your units do your heavy lifting. And if frequency is in meters, wavelength is in meters, and frequency is in what? Per second. Okay, so if wavelength is in meters and frequency is in per second, do you see where we end up with meters per second? Okay, you end up with a speed, and it will be constantly the speed of light. What's the variable for the speed of light? C as in cat. Yes. So it's a kind of neat little trick, and it's not really that much of a trick. Okay. Oops, did you guys get that? I guess there was one more. So I'm hoping you get, because wavelength is very important. You want to know what sort of wavelength you have coming at you with regard to that energy. And that is this symbol right here. This is wavelength. Okay, times F for frequency is equal to C for any cousin. All right, cool. Well, focusing in on the energy that we care so much about, it's funny because when I get to this chapter, I'm like, oh my gosh, there's all that energies out there that we are just like oblivious to. They're not, okay, so it's not like ghosts or anything, but I mean, it's just energies that we just kind of blow off. We use our microwaves, we go to the dentist, they take an x-ray. But, so if we focus on just the visible part of light, the acronym, or kind of the mnemonic device, is not acronym. The mnemonic device, like a name, first name Roy, middle name, initial is G, last name is Biv, B-I-V. That will give you the colors of the rainbow in the right order. Because the colors of the rainbow change just because of their wavelengths. So up here, in order for my Roy G. Biv to match up with this, I have to go backwards. A cool thing about this is, do you see a little bit longer than visible is what's that? Red, right. So, and a little bit shorter than visible light is ultraviolet, exactly. So actually, if you kind of think of it like that, you're ready to go ahead and write Roy G. Biv backwards. See how that works? Okay. Well, red is the longest wavelength color, longest lambda, least energy, and violet is the shortest wavelength.
Indigo's darker than violet, right?
Indigo, I do not get that color. Indigo is between violet and blue. I kind of think as violet is kind of a, and indigo might be kind of a darker color. With colors, there's different aspects of color, the hue and the intensity. I don't know. But I don't know if this is true or not, but let's count them. 1, 2, 3, 4, 5, 6, 7. 7 colors, Roy G. Biv. I don't know if this is true or not, but I heard that Newton didn't want there to be 6, so he inserted the indigo. It's like, I don't know if that's true or not. Okay. So we good with that? Visible light's very important to us, and so kind of honing in on visible light, that's what we got going on. And I could bring this up, but all it would do is when I move this slider, the frequency and the wavelength change. Okay? Now, the speed of these cousins, the speed of all of these energies, does it change with the energy? No, it does not. These speeds at which these things propagate through space or move through space, the speed of all of these guys, speed is equal to c for all of them. For all. One for all. Okay, so let's do this. There's just a couple slides on atoms, but let's go ahead and take a running start at this on Friday. Okay? Any questions? Cool. And you'd be like, why do we need to talk about atoms? You're like, dude, you're so getting into your chemistry. When you talk about atoms, because basically these energies interact with atoms different ways, and we kind of need to know a little bit about atoms. Okay? So that will be on Friday. And so this gives us a little bit of time if you want to go get lunch. Okay? So review session at noon.